Welcome to this quick tutorial video introducing the MGS Destriping plugin developed by Estimages Geostatistics for seismic interpreters using the OpendTect Pro software. This noise attenuation example is based on the Open3D seismic dataset offshore United States Atlantic coast named Black Ridge. As you can see on this subvolume, an inline footprint impacts the dataset. Based on a decision tree specifically designed to help the user understand how the Estimages plugin works, we will clean this data in an optimal way through this short video. First of all, it is important to know that in the case of structural footprints, our plugin works best on datasets where the geology is subhorizontal. For energetic footprints, the plugin functions optimally, independent from the geological setting. For a complex geology with the presence of structural footprints, we recommend to ask our team of experts for a tailored noise attenuation solution via contact@estimages.com. This said, we can review the Estimages suggested workflow for using the plugin. Step 1. Calculate an energetic attribute. Here, we choose the RMS attribute. If any footprint appears on the attribute, you are dealing with at least an energetic footprint. To filter this noise, the plugin needs one parameter from you, the footprint width. An optimal way to identify this parameter is to measure the period of the noise with the OpendTect measuring tool. Preferably, choose an area where you can clearly see the periodicity for this noise. You can choose to measure the period between either two troughs or two peaks. Make sure to use the time slice view in the 3D viewer to avoid measuring an apparent distance. Then, dividing the measured distance by 2 will give you the footprint width. Here, I got approximately 150 meters. Open the Estimages plugin window. Choose the type of data you wish to filter, the footprint type, the width you just determined, the footprint direction, inline here, and choose the name for the output. Estimages gives you the option to compute the extracted artifact. Check the footprint box to get it calculated at the same time as the filtering process is running. For visualization, you have the choice to display either the destriping component corresponding to the filtered result or the footprint one corresponds to the extracted artifacts. Here, a footprint still remains on the data, whether looking at a time slice or a cross line. The decision tree suggests that another kind of footprint remains, a structural footprint. In order to highlight its presence, you can calculate a structural attribute. Here, we chose the semblance. The footprint in this case is very narrow, as you can see on the crossline section. You can tell that it relates to the seismic bin. For Black Ridge, it corresponds to 75 meters. We will thus choose a width of 80 meters to make sure that the algorithm can identify the noise during the process. Open the plugin window one more time. Choose the output of the first filtering as an input. Enter the footprint type here, structural, the width, the footprint direction, and run. The result displays a major improvement compared to the raw data. We will quickly calculate the difference between my second filtering and the raw data to get an idea of the removed artifact to quality check the results. As we can see here, we removed nearly all of the footprint without harming the signal. We are now ready to use the auto-picking tool with fewer seeds needed thanks to the noise we just extracted with the Estimages plugin. A quick side note, when you're facing isolated patches of noise and the periodicity is not clearly visible, you can measure the half period on the patch which directly equals the footprint width. This is how. From one side of the patch to the other, identify the jump between two minimum variable values. The measured distance here corresponds to the semi-period. Write down that figure and enter it in the footprint width parameter required to filter.